So last time we saw how we can turn a differential equation into a difference equation, a form that we can feed into a computer to obtain a numerical solution. And we worked through the example of the heat equation that involved a couple of derivatives, a derivative with respect to time, and then a second derivative with respect to position. The way we transform a differential equation into a difference equation is just through this prescription. You take the value for x, your position in space, replace it with a value along a grid. So J there just indicates the unit you're at along the grid. So x0 is all the way over to the left, x1, x2, x3, x4, etc., all the way over to the right, however far you're considering. Then we've got to do the same thing with time. So as the function evolves in time, we need to replace this continuous value t with discrete values tk. So the k there indicates which frame of the animation you're in, k0, k1, k2, etc., moving forward in time one step at a time. That means whatever function you're looking at, last time it was temperature, today it'll be this thing psi, whatever function you're looking at that's a function of x and t is going to be replaced by a thing with two indices, u, j, and k. So the j tells you which point you're at along the grid, and k tells you which moment you're at in time, which frame you're at in the animation. And we had a couple of derivatives here that we need to replace too. So the prescription is you take this du dt and you replace it with a difference based on time. So you keep the j's the same and you go from k to k plus 1, the current frame to the next frame, and divide by dt, your time step. Then you do a similar prescription for the second derivative with respect to position, the concavity of the function. So you take your point to the right and a point to the left. You leave k the same, right? You're only varying x now, you're not varying t, so you leave k the same. So you go a point to the right, j plus 1, a point to the left, j minus 1, and subtract 2 times the function at the current point, jk. Then you divide that by dx squared. Why the squared? Well, because this is a second derivative, not a first derivative. So first derivative gets dt to the first power, second derivative gets dx squared, the second power. And that's wonderful, and we had some fun with that with the heat equation. And now what we're going to do is turn our attentions to the Schrodinger equation. So this is the equation that governs everything you do in quantum mechanics. If the Schrodinger equation is all about this thing psi, the wave function. I did not mean to put a function of x there, excuse me. This psi here is a function of x and t. A lot of textbooks will have this as a capital psi. I'm using a lowercase psi because I can write lowercase si's more neatly than uppercase si's. This thing is what we call the wave function. It is the function that governs the state of whatever particle you're looking at. Usually you're looking at an electron. So this is the function that has all the information about where the particle is likely to be found, how fast the particle is likely to be moving, how much energy the particle is likely to have. And I keep saying likely because this psi is related to the probability. So if you take the modulus of this psi and square it, and we'll review what modulus is in a second, just think of it as a fancy way of squaring, or a fancy way of taking absolute value. This thing gives you the probability density of the particle's position. In other words, when you take psi squared, wherever psi squared is at a maximum, that's where the particle is most likely to be. Wherever psi squared is near 0, that's where the particle is least likely to be. Because in quantum mechanics, as you will soon learn, we don't have a definite location for particles anymore. We have them sort of spread out in space in terms of probabilities. Now you might be wondering, if psi squared is the thing that tells you the probability, why don't we just work with psi squared? Well, because the Schrodinger equation isn't written in terms of psi squared, it's written in terms of psi. And we'll get into why that is in just a minute. There's a few other pieces to this to look at. H bar here is something we call Planck's constant. You probably met Planck's actual constant h at some point in a physics class. This is just h divided by 2 pi. Basically, we get tired of writing h over 2 pi, so we just put a bar on h. But this is the thing we use more often, so we tend to call this one Planck's constant instead of h. We could probably get into arguments about that in the comments below. But yeah, h bar, we're just going to call that Planck's constant. It's a teeny tiny number, and that's the important thing. M here is the mass of the particle. Again, usually an electron. It could be some other subatomic particle, but usually it's going to be an electron that you're working with. V of x Here is the potential energy. So this is just a function that exists everywhere in space. It tells you kind of how high the particle is at that point in space. You can think back to potential energy in terms of gravitational potential energy, or a spring's potential energy, or gravitational potential energy out in space. It works the exact same way you saw in classical mechanics. It plays a little bit different role here. Then we come over to this side. You've got a derivative. Well, we know how to handle derivatives. You've got h bar again, and then you have this thing I. And honestly, if it weren't for this I, this equation would be a lot easier to work with. There's only one of it in the entire equation, but it really is going to throw us for a loop in a second, and I'll show you why. This I is the imaginary unit square root of -1. And I was so happy when we finally got to this in high school math, because in middle school, they told me, oh yeah, there are square roots of negative numbers, but those are imaginary numbers. And I said, what's an imaginary number? So imaginary numbers show up whenever you have this square root of -1. The way it works is this psi has to be what we call a complex number. The way you write a complex number is as two parts. You write it with a real part and an imaginary part. And the way you combine those, multiply the imaginary part by square root of -1, and then add those two pieces together. Now, here's the thing. Because of this I here, because of this one I, psi has to be complex. So this wave function here, it has to be a complex number. It must give you a complex number. Let me show you why that is. Let's suppose you wanted to have just a real wave function, right? Let's suppose you just had psi equal to a real part plus 0 imaginary part, right? Let's suppose you wanted to construct a psi that was only real. Well, let's take a look at what happens with the Schrodinger equation. So you would have negative h bar squared over 2m, d squared real part, dx squared, right? Because there's no imaginary part, so psi is just equal to a real part, plus the potential energy times the real part would have to equal I h bar d real dt. And this is the part where you run into a problem, because Planck's constant's real, mass of the particle is real, r is real, x is real, v is real, r is real. This whole side is real, right? You come over here, this piece is real, this piece is real, this piece is imaginary. So our initial assumption has to be wrong. This psi has to be complex. You can't get away with making it real. Trust me, if we could, we would, and we would dispense with this whole complex number business. But because of this I that's here in the equation, psi has to be a complex function. That's actually, we can use that to our advantage, because what I can do is I can take the Schrodinger equation, the actual Schrodinger equation, not this monstrosity over here. I can take the Schrodinger equation and I can turn that into two separate equations. Let me show you how. All right, so here's the original Schrodinger equation. What we're going to do is plug in for psi its real part plus I times its imaginary part. Now, there's going to be some messy algebra along the way, because you know by now that a physics equation has to get messier before it gets neater. So we're going to get the equation a little bit messy, and then I'll show you a trick to make it a little more neater. So we've got our minus h bar squared over 2m, d squared dx squared. Now I can plug these in for psi, right? And when I take a derivative, the derivative just distributes to each piece. So I'll have a second derivative of r plus I second derivative of imaginary part with respect to x squared, right? All I've done is taken this psi and replaced with r plus I capital I, right? The derivative just distributes. The I comes out because it's just a constant. Plus I'll have v, then I'll have real part plus I times imaginary part. That part is pretty straightforward. Then I've got equals. Here's where it becomes the interesting part. So I've got an I h bar. Now I need to distribute this d by dt to both of these pieces. So I'll have a dr dt plus I di dt. Right, again, I've just taken the derivative, distributed it to both pieces here. Now comes the interesting part, right? Because I have an I here, and an I in here. You really only want to have at most one I per term, right? You either want to have 0 I's or 1 I. If you've got 2 I's on here, whenever you have I times I squared is -1. And it's always amazing to me. Students will know that I equals square root of -1, but then when you put an I squared in front of them, they so rarely turn that into a -1. This is a habit you need to get into, that if you see an I squared, replace it with a -1, because that's a lot simpler than having a bunch of I's running around. What that means for the right-hand side here, if I distribute this, I'll have an IH bar d real dt plus I've got an I times I, again that gives me a -1 h bar di dt. And you say, well gosh, that looks worse. Let me show you how we can make this better. I'm going to take the pink chalk here, and I want to underline everything that is real, right? So I want to underline everything that does not have an I. So I come to this and I say, okay, this doesn't have an I. Right? There's no I's here. There's an I here. I'm not going to underline that. This part does not have an I because this v is real. V is not carrying any hidden I's. It's a real function. This part does not have an I. Now I'm going to take the blue chalk and I'm going to underline everything that does have an I. This thing has an I. That thing has an I. This part has an I. Right? We're going to ignore this middle term over here, right? Here's the thing about complex numbers. When you have one complex number equal to another complex number, I know this thing is lengthy, but ultimately this is one number and another number. Every equation is just one number and another number. When you have one complex number equal to another complex number, the real part on one side has to equal the real part on the other side, and the imaginary part on one side has to equal the imaginary part on the other side. There's no other way it can work, because only the imaginary part has I's, and the real part has no I's. It's apples and oranges again, right? It's like when you have X's and Y's on one side and X's and Y's on the other side. The only way they can match is for the matching terms to be equal. So what that means is all the pink terms have to be equal to each other, and all the blue terms have to be equal to each other. So let's start with the pink. All right, let's start with minus h bar squared over 2m d squared real dx squared. There's my first pink term. Plus potential energy times the real part. That's my next pink term. Equals, now I need to come to the pink term over here. Negative h bar di dt. This is a whole lot simpler than all of this, right? Because this thing, this second line equation here is a whole lot to keep track of. This, there really isn't that much to keep track of. And it's actually kind of nice, because on this side, I've only got the real part of the wave function, and over here I've got the imaginary part of the wave function. So what this is telling me is that the real part and the imaginary part of the wave function are actually coupled together in a very interesting way. Because the rate of change of the imaginary part, this di dt, depends on the concavity of the real part. Let's see if we can get something similar going the other way. So now let's take all of the blue pieces. Right? So I'm going to have a minus h bar squared over 2m d squared I dx squared. Right, that's my first blue piece over here. I want to have an I coming along for the ride. Plus, need my blue piece here. I have I potential energy times the real part. Going to equal, now I need my blue piece over here, IH bar dr dt. Boy, those look similar, don't they? One of the glaring differences is that this thing, everybody has an I, this thing, nobody has an I. But if everybody has an I over here, I can cancel them, right? It may be an imaginary number, but it's still a number. I guess I'll cancel it like that. It's not 0, so I'm allowed to do that, right? And so here we see something interesting. I've got the same relationship between R and I here that I had between I and R here. Oops, and I made a copy error. This was supposed to be an I. You've already been yelling at me in the comments for 30 seconds. There we go. So this is where this gets interesting, because I, the rate of change of I depends on the concavity of R. The rate of change of R depends on the concavity of I. So they've got this kind of like mutual inductive relationship, right? If you've had E and M, this is like electric fields and magnetic fields, right? One induces the other, then induces the first, then induces the second, etc. They've got this nice cyclic relationship going back and forth. They don't blow up, though, because this one has a minus sign, this one does not. And that's why this has to be complex. Because of this I squared equals minus 1, with complex numbers, when you've got i's multiplying around, you'll always end up with an extra negative somewhere compared to the other equation. Because this one has a negative and this one doesn't, they feed off of each other and kind of cycle around each other instead of blowing up, right? Which is good, because we don't want our electrons to blow up. That would be bad. All right, so I've got my Schrodinger equation separated into two equations based on the real part of the wave function and the imaginary part of the wave function. The reason I want to do that is because I would rather my computer program be dealing with real numbers. You could put this in and use a complex number package and hope that it all works out. But this way, I'm avoiding using complex numbers when not necessary. So now what we're going to do, we're going to apply our difference equation prescription, the thing we did for the heat equation, we're going to do to both of these equations. Because the Schrodinger equation is really two separate equations, I have to apply the prescription twice. Once to this, involving r on the left and I on the right, and this involving I on the left and r on the right. So let's start with this piece over here first. So I've got a minus h bar squared over 2m, right? That doesn't get any of the j's and k's because it's just constants. Then I've got my second derivative here. So I need to use my second derivative prescription here. So I'll have a real j plus 1 comma k plus real j minus 1 comma k minus 2 real jk. And all I'm doing is taking the u's and replacing them with r's, right? And I'm going to divide by dx squared. Then I need to do the same thing for v. I'll have v at j. Remember, this potential energy is just a function of x. It's not a function of time. You could make it a function of time if you wanted to, but usually it's just a function of x times r jk. Going to equal, now I need my negative h bar di dt. Okay, my di dt, I take this part of the prescription, the time derivative, and we're going to replace that with I j k plus 1 minus I j k minus 1, going to divide by dt. And again, this difference equation has all the same information as this differential equation, right? Because if I get a maximum in R, right, if I get a point that's higher than the others, that's going to make this thing negative, will make this whole thing positive. So I'll get a, well, if the negatives cancel, so I'll have a negative for di dt. Same thing here, I'll end up with a negative, a decreasing value of I if I have this piece higher than the other two pieces. It's a little more complicated than the heat equation because of this potential energy, but really if you took away that potential energy, it's really the same thing as a heat equation, right? You've got this, this second derivative with respect to position, first derivative with respect to time. The only difference is you've added this potential energy, and now we're going between two coupled functions. But other than that, in terms of features, it's quite similar to the heat equation, right, in terms of how the derivatives work out. All right, let's do the same thing now with a little bit of space for our second equation. So I'll have minus h bar squared over 2m. And now I need the second derivative of I with respect to x. So that's going to look just like this. I just replace the r's with i's. So I j plus 1k plus I j minus 1k minus 2I jk. Then divide by dx squared. Plus vj ijk. Right? This piece is the same, this piece is the same. Now we get to the only piece that's different. Right? Equals positive h bar. I'll put a positive there just so we remember. Now I need the derivative of r with respect to time. So r j k plus 1 minus r j k minus 1 divided by dt. So it's useful to note here that these equations look very similar to each other, right? I've got a minus h bar squared over 2m. I've got a second derivative. I've got potential energy times a function, potential energy times a function. I've got an h bar time derivative, h bar time derivative. The only difference, literally the only difference besides switching around the j, the real part and the imaginary part, is this sign. Right? That's literally the only difference between these two pieces of the Schrodinger equation, which is useful because, you know, things should be symmetric, and that makes it a little bit easier to put in the computer. Hey, speaking of putting it into the computer, our next goal is going to be to solve for each of these pieces the wave function at the next frame in time. All right, so this over here is my starting point, right? I need to take each of these equations, solve for this piece here. There may be a lot of terms, and there may be a lot of adding and multiplying and dividing going on, but it's just algebra at this point, right? We are skittering around the calculus through the use of a difference equation. So let's start with this first one. Let's start with equation 1 here. So I want to get this thing by itself. So kind of like we did last time, we'll start by moving the constants over, this dt over negative h bar. So I'll have a dt over h bar. I'm carrying with it a negative, but it's going to get multiplied by this negative here. So I'll just have a net positive, h bar squared over 2m. Then comes my r second derivative, r j plus 1 k plus r j minus 1 k minus 2r jk. And actually I can make that a little bit cleaner just by putting dx squared in the denominator out here. Then I don't need the huge parentheses. Anytime you can avoid huge parentheses, it's worthwhile aesthetically. Plus, I've already got the vj rjk, right? Now I need to multiply by the dt over h bar, which carries with it a minus sign, right? So I'm taking dt over h bar, negative, multiplied by that thing. My goal ultimately is to get this piece, right? This ij, comma k plus 1. So it's I at a point in the grid at the next animation frame, at the next moment in time. I need to get rid of this piece, so I just add that on over here. Plus I, j, comma, k, minus 1. Excuse me, those are not supposed to be negatives. Oops. There we go. We cannot go backwards in time. We can only go forwards in time. There we go. Okay, so I have the new value equals the old value plus the change. I've unfortunately written it backwards, but you know by now that addition, you can move things around. Then we need to do the same thing with equation 2. So equation 2, let's see if we can follow the same prescription here. So I need to take this dt over h bar, multiply it over here. So I'll have a dt h bar squared over dx squared h bar 2m. But this time I have a positive here and a negative here. So this whole thing is a negative. The same thing here, but with imaginary part. I, j plus 1 k, plus I, j minus 1 k, minus 2 I, j k. Then we'll have the same kind of setup over here. We'll have a positive dt over h bar, vj, ijk. Right? Let's see, I have a positive here, a positive here. There's no negatives entering in there. Okay. I've run out of space. We'll just continue down here. I need this thing to ultimately equal this rjk plus 1. Right? The next moment in time. So we'll just add on to this rjk. And again, you look at the equations. You look at the parallel parts. So I've got real part replaced by imaginary, real part replaced by imaginary, imaginary replaced by real. I've got all my j's and k's lining up. I can clean this up a little bit by erasing an h bar and an h bar squared, erasing an h bar and an h bar squared. And now I've got this in a form that I can put into the computer. It may be messy. I may have run out of board space, but I can put this into a computer, right? I just need a line here and a line here. And I just need to loop over it just like we did with the heat equation. All right, so here's the code where we implement the difference equation version of the Schrodinger equation. First, we're going to set up a potential energy function. We're going to use the harmonic oscillator x squared here. This is a classical one to test. Then we need to enter our initial wave function. Remember, you have to specify psi at time t equals 0 at every point in space. So for that, we're going to set a psi real at time t equals 0 and a psi imaginary at time t equals 0. So psi r is psi real, psi I is psi imaginary. And you notice these are only functions of x because time has been set equal to 0. And so here we're going to have a Gaussian that's been shifted to the right a little bit. And here we're going to set the imaginary part equal to 0. You can actually almost always get away with having an initial real wave function. I could be mistaken about that being always, so I'm just going to hedge and say that you can almost always get away with it. I'm sure there's some counterexample out there somewhere, but you can almost always get away with the initial wave function being real, even though the wave function as a function of time has to be complex. So then here we get into the difference equation information. So this is just like we had last time for the heat equation. We've got dx and dt set up. And then here we've got our quantum mechanics stuff. So we've got h bar, the mass, and the initial time. We're going to set h and m to be 1. We really will not be playing around with those very much. If you wanted to change them into real world values for an electron, you can. But we really are not going to play around with those very much. It's really this potential energy and the initial shape of the wave function that really determines how the problem behaves. All right, then we need to enter a range for x and for time. So x min and x max, we can usually get away with a range like this, -3 to 3. There's rarely a reason to go out to 1,000 or something like that. T max I've set equal to 5 just so that the code will stop running at some point. You can make that larger if you would like. Here we've got some graphing options. We have not discussed what these are yet, so we're going to set those equal to false, and we're just going to skip over everything having to do with the graphs today, and we will come back to those in a future episode. Then we need lots of lists. So you remember for the heat equation, we needed 2 lists. We needed the temperature at the current time and the temperature at the next time. Well, here we need lots of lists because we need our list of x values, right? So this is xj for the difference equation. We need 2 lists for the wave function itself. So I need psi real and psi imaginary, right? Because it's 2 different parts. There's psi real part and psi imaginary part. Then I need to be able to store the modulus. So this is that absolute value square. It's going to be psi real squared plus psi imaginary squared. It's straightforward to calculate, but it will save us some time in terms of computation if we go ahead and calculate it and set it in this list. And then I need a list for the potential energy because I don't want to have to keep calling back to the potential energy function. It's not changing. The values aren't changing. So we might as well just put it all into a list at the beginning. Save ourselves a little bit of computer time. And then I need the values for the next frame, for the wave function at the next step in time. And so this is the real part of psi at tk plus 1 and the imaginary part of psi at tk plus 1, right? So all of these are there to get all the j's. This is here to move us forward in the k index and along the time. Here's where we create the graphs. We're going to skip those for right now. We'll talk about this in a future video, but the wave function always needs to be normalized, meaning the total integral underneath it needs to be equal to 1. And it's not a trivial problem to get your wave function normalized to begin with. So rather than do that, we're just going to divide by the normalization and force it to have a normalization equal to 1. Let's see, here we will talk about the graphs a little bit. We're going to graph a few things over here in this window. We're going to have the real part of the wave function, the imaginary part of the wave function, the modulus of the wave function, and we're going to graph the potential energy. Now, the potential energy has different units than all of these, so you technically shouldn't have them on the same graph, but it's very common to put them on the same display. We're just going to scale it by their maximum values here so that it'll fit on the same graph. Just please understand that it has different units. Okay. Here we are getting into measurement stuff. We're going to skip over that for now. We'll come back to that in a future video. That actually takes up a fair chunk of the code, so you can just skip all of that. We're going to come all the way down to line 216 where we iterate psi forward in time, right? So this is where we set up our difference equation. Here in lines 221 and 222, we've got our iterative equation. It takes up my entire screen here. So the next value equals the previous value plus the change. And so here we've got our real part. We've got our next real part equals the current real part plus the next step forward plus the change. So here we've got that negative h bar dt over 2m dx squared, right? That's all those constants we collected out in front. Here we have the imaginary part. So here we've got the spatial derivative, the second derivative of the imaginary part with respect to x, right? So psi r only appears here. The rest of it is psi i's because of the way they're coupled together. Then over here we've got the potential energy times dt over h times the imaginary part. Then we come down here and we've got kind of the flip of this equation, right? Because we've got our imaginary part over here for the next step, the imaginary part for the current step. We've got our h bar, dt, blah, 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 same stuff. But this time we don't have a minus sign in front of it, right? So the signs are flipped over here because of the way that that I ended up distributing. We've got flipped signs over here. And so we've got the second derivative of the real part with respect to x and the first derivative of the real part with respect to time. And so this is the difference equation. For all of the other baggage that we have in this code, this is really the central physics. This is the thing that's going to help us learn quantum mechanics by animating the wave function for us. And then down here, just like we did last time, we're going to clear the graphs, we're going to redraw them, etc. So let's go ahead and run this and see what it ends up looking like. So here we've got our wave function. Here I've got a little key for you. So the red is the wave function's real part. The blue is the wave function's imaginary part. We started out with all real part and no imaginary part. So we started out with a flat blue and a curvy red. And so the green was basically equal to the red because there's nothing being contributed from the blue. But what you notice is happening here is that sort of weighting is being shifted between the real part and the imaginary part, right? So weighting is leaving the real part. The real part's getting smaller here. And it's being shifted to the imaginary part. So the imaginary part is picking up a little bit more shape here. The real part is getting a little bit flatter. It's also moving a little bit to the left. We'll talk about why that is in a future video. But the important thing is that this modulus maintains the same basic shape, right? So the modulus is the red thing squared plus the blue thing squared. So even though weighting is shifting back and forth between red and blue, the modulus, the green part, gets to stay roughly the same shape. It gets to stay roughly, it's not constant, we are going to see it move, but it gets to stay more or less consistent in terms of its shape. But what you do notice is happening to the modulus is that it's starting to move to the left a little bit. It's starting to move to the center because the center is where we've got a minimum in the potential energy, right? The potential energy, the black curve, has a dip in the middle. Particles tend to move toward lower potential energy regions, right? Things roll downhill. It's basic physics. Well, it's showing up here in quantum mechanics as well, but it's showing up in the modulus of the wave function, which is why we're so interested in the modulus, because that's the thing that obeys, or at least tends to obey, our classical physics laws. Well, I hope that's a good first look at the quantum mechanical wave function for you. Next time, we're going to see what happens to this wave function when we start taking measurements of our position and momentum. Thanks so much for watching. I'll see you next time. Bye-bye.